So yeah, my name is John Potocny, and this is Profile All the Things using pprof and Go. Real quick, has anyone never used pprof before? Raise your hand. Okay, fair number of people. All right, cool. So we're going to cover some of the basics really fast and gloss over them. I'm going to go into some of the. I'm going to cover enough so that you're not left behind. But if you want to get like a lot of detail on using pprof, there's a ton of resources on there on the blog and the Go doc and everything for getting started with pprof. But I want to cover some of the things that aren't covered as often, so that the stuff that you might have questions about later, you're going to have a resource for. So that being said, let me do the real quick corporate boilerplate. So I'm a backend developer at VividCortex. We are a database monitoring startup, and we monitor MySQL, Postgres, Redis, and MongoDB. We are hiring backend devs. Our entire backend's written in Go. So if you like writing Go code, you like databases, you like monitoring, come talk to us, or my colleague Amanda's outside at the booth handing out animal hats. So yeah, cool. So let's actually talk about pprof here. So pprof is not something that's specific to Go, but it's built into Go's tooling. So it is a profiling framework we can use to visualize how our programs are behaving in different ways. It's been around since the beginning of time. Since before Go 1 was released, we had support for generating profiles. Initially, it was just CPU profiling and heap profiling. Now you can see the full list as of Go 1.8, so there's like 6 different profiling formats that are supported. And there's a link to the Go doc for reference. Let's see. So if you've never used pprof before, I've got full examples on how to use it. So there's a playground link that we'll jump out to. So here's an example of creating a CPU profile here. You just create a file to write to, call pprof.startCPUprofile, and then you just defer stop CPU profile. It's going to write out a bunch of data about how your program is behaving. When the program exits, then you've got all your data. Similarly for profiling heap, create a file, and then we just defer a function for this. There's no startup. Is to pprof.writeHeapProfile. Really easy. So getting started with writing your own profiles is just that simple. There are basically analogous examples in the Go doc as well. So if you need a reference to this, it's readily available. Get that in here. Alternatively, if you've got a service that just runs persistently, you can import net/http/pprof. So you can see a picture right here. Just use the underscore. We don't need to do anything with the package. It's going to initialize some HTTP handlers for us with the default cert mux in Go. And that gives you a nice little website that you can go look at. So here's debug/pprof on the left. And that shows you all the profiles that are available. If you're using a custom router like HTTP router or Gorilla, you can go ahead and register these handlers yourself. I find it easier to just go ahead and spin up a separate server on its own port. And that way you've got your diagnostic internals on its own system. You can kind of keep that closed off against your application. You don't have to worry about things getting mixed up or anything like that. And all of VividCortex's apps actually have their own pprof server running in production. So it's not like a lot of overhead to start one of these things up. It's just overhead to use them. So you want to know how your programs are behaving. Take a little bit of a hit to get that more instrumentation. So once we've got a source of data, either a file or a URL that we can hit up, you call gotool pprof. So here you can see an example. I'm just calling pprof against one of our apps at VividCortex and grabbing a CPU profile. And once you do that, you get an interactive shell. You can go ahead and type commands, get different visualizations. So top just gives you the top 10 CPU users in my application. So you can see here, I'm spending a lot of time in JSON coding tab. Side note, GoTest has CPU profiling and memory profiling built into it. So you can see an example here where I do GoTest CPU profile equals a file name, and then I can run pprof against that, get all the information about my test binary, or if I run benchmarks, I can see what the hotspot looks like. Pro tip, if you're using a API URL, you do not have to specify a binary in the argument to pprof, but you should. It will give you more details. So by default, you can get function level granularity about which functions are being called at most time. If you add the binary, then we can look up what source lines are responsible for overhead. So here's an example where I'm using something called the list command. It's actually showing me the output from my source code, and I can see here's my HTTP handler. It's just writing out the value of a counter, and I can see exactly which line and which function calls are causing my overhead. So that gives you a lot more data. If you've got big functions, it's especially useful. You can even get instruction level granularity. So if you want to look at the assembly output, that is something that you are able to do. So here's where we're going to start moving a little bit faster. I'm going to iterate through the types of profiles. So CPU profiling, not a whole lot to say about that. There's a lot of literature out there. It shows you which functions are spending the most time in your program. So here's a call graph of CPU utilization, one of the programs in VividCortex. Not that interesting. It's basically, the most frequently talked about one. It is different from the rest of the profiles in that it streams data out to a file, where the other ones are going to be instantaneous lookups. So that's one thing that's unique about CPU profiling. But that's about all I'm going to say about that. So next we got heap profiling. So we want to know how is the garbage collector doing, how much memory are we allocating on the heap. And so we got a few different ways that we can view this information. So there's 4 different modes that you can specify when you call pprof and grab heap data. We can look at in-use memory in terms of space allocated for a number of objects that have been allocated on the heap, or we can look at allocations over time since your program started. So that's those last 2 flags, alloc objects and alloc space, show objects and bytes allocated respectively. So if you want to see where most allocations are coming from, you get GC heavy program, or if you want to know why you've got so much memory being allocated, you can see this coming from the heap and specifically where it's coming from. So very useful for debugging memory leaks or again, just high GC overhead. Go routine profiling. This is one that's not talked about as much. It's incredibly useful. You can get a list of go routines aggregated by stack. So I can say, I've got 5 workers that are all running the same function. So I've got an HTTP handler, then I know which handlers are active at any moment in my program. If you pass debug equals 2, it will give you a full stack dump of all the go routines running in your program and their current state. So I can see if something is waiting to read on the channel, if it's blocked on network I/O, if it's runnable but not running, or if it's actually running. So you can get information about what's going on. This is really useful for diagnosing deadlocks. That's why I actually started getting really interested in pprof, was diagnosing a bunch of deadlocks we were finding in our internal services at VividCortex. So super useful to have if you're trying to figure out what's going on with the application, why it's locking up or not doing what you expect, and see the state of everything. I added thread create for posterity's sake since it's listed in the list of profiles that are available. It turns out that thread create is actually broken. So if you're wondering why all of your thread create profiles look blank, it's because it doesn't work. It hasn't worked since Go 1.2. So it's supposed to show you which Go routines led to the creation of threads in your application. As of Go 1.2, we had a scheduler redesign, and the scheduler is responsible for the creation of all threads. Regardless of what action you're doing, the actual scheduler runtime is the one that's creating new threads for your application. The runtime does not show you threads that are created by the scheduler, because why would you want to see that? It's not useful context. So you don't actually get the information that you want from the thread create profile. It doesn't tell you what action caused you to spawn a new Go routine. In general, if you're trying to diagnose lots of threads in your application, file I/O and syscalls will cause threads to be generated. So keep a lower bound on how many of those you do simultaneously, and you won't have too many threads in your app. So, yep, it doesn't work. That was really, really frustrating to find. Okay, so block profiling. This is a really nice one to understand why your app is not scaling the way you want it to. You want to see how long Go routines are spending blocked and what they're being blocked on, whether it be waiting on a mutex, channel operations, I/O, whatever. We can see it in block profiling. This is not enabled by default. If you spin up an HTTP server with pprof, you'll see it listed, but it'll have no data. So in order to turn it on, you need to call runtime.setBlockProfile rate to enable it. And the argument is just a rate in nanoseconds to sample blocking events. 1 is sample everything. Otherwise, you specify just whatever rate you want. So for example, 100 will sample every 100 nanoseconds. I think that's what CPU profiling defaults to. So here's an example output. So I've modified my HTTP server and added a time.after operation to make it a little bit more significant blocking. And you can see there's 2 operations in the code here that block. We've got the time.after channel wait, and then we also spent a little bit of time blocked on IO.write string. So our network operation to return the result back to clients is blocking for us. This is a local host app, so it doesn't spend anywhere near as much time as the channel hop. But if you're doing real work, then you can see time spent writing your payload back to a client with the network causing blocking. Also, again, channel operations, mutex contention, anything you're doing that's going to cause a Go routine to have to stop and wait. So the last type of profile that's available by default is mutex profiling. And this is kind of similar to block profiling, but they're different in a fairly significant way. So this was added in Go 1.8, by the way. The block profiling shows us which routines are blocked and how long they're spending blocked. The mutex profile shows us which go routines are spending a long time holding on to a mutex. So it's showing us the blockers instead of the blockee. So if you got a mutex that's in a hotspot in your application, you can see what go routines are acquiring it, what's going on inside that critical section, and why it's taking so long, and your app is getting serialized. So again, it's disabled by default. We call runtime.set mutex profile fraction to enable this. It ends up being about the same thing as the block profiling arguments. If you set 1, it will instrument every single mutex contention event. If you set 100, it's 1 in 100 events. So pretty much the same thing, but we call it a fraction instead of a rate. I don't know. Someone wasn't thinking when they added the API. So yeah. And so here's an example. I've modified my program again, and I'll actually switch out here and show you some code to give you an idea what it looks like. So I've got 2 endpoints. One is incrementing the mobile counter by mutex, and the other one is just reading its value back. So you can see here's the increment operation. We're doing a counter increment in a critical section, but incrementing in a named reserve path, so it's not generating that contention. And then down below, I'm blocking my mobile counter and writing the response inside the critical section. So this is going to generate a lot of contention. And if we go back to our slides, you can see this is what it looks like in handle read counter. We're seeing time associated with the unlock operation. That's when we release the mutex, so that is basically all the time accumulated up to that point is the critical section. So in this case, I can see it all on the line. Maybe a longer critical section, you might have to go back and scroll through your code. But that's how the profiles are oriented. So I can see here, if you want to speed things up, I can read the global counter.count and then do the IO.rate string outside of that. That'll give me some more scalability. Quick note on mutex profiling, this is new, it has some drawbacks. If you use an RB mutex, the rlock and runlock functions are not instrumented. So RW mutex.lock and unlock are instrumented, that will work, but if you call rlock and runlock, there's no visibility around that. So I modified demo 3, which we were just looking at, to use rlock and runlock to grab this pprof output. You can see it just shows you nothing. We're not spending any time instrumenting mutex functions, so we don't get any contention. There is an open issue with a milestone for go1.9 to fix this. I don't know if it's been fixed yet or not. I hope it will be fixed before the release, but the freeze is coming up, so we'll see. So this is not all the profiling we can do. There's actually an API for us to create our own profiles. So if you've got an application resource that you want to track, we can go ahead and set that up. So you can see a little bit of code block here to set up your own custom profile. You just declare a pprof.profile, and then you create it calling pprof.bprofile. The trick here is that if you try and create a profile twice with the same name, you will get a panic. So you want to do this kind of pattern that I've got in my init function, where we look up the profile name, make sure we don't get anything back, and then initialize it. We already got something, we're good to go. And you can see it'll automatically add your custom profile to the list of available profiles in your net/HTTP handler. So that's really nice. There's no added work besides initializing the profile and creating it. So once we've got a custom profile, we need to do stuff with it and add instrumentation. So I'm adding an active request tracker to my demo program. And let's go ahead and jump back out and look at some code here. So here's that init function we were looking at. And same thing as we had before. I've got 2 endpoints. And I have the helper here to track this request. So first thing we got to do is we need a unique key for each request. So I'm just initializing a pointer to a byte. And I'm going to use this memory location as my key. Very simple. Once I've got a key, I call myprofile.add. And this is basically the same thing as you do when you're adding a value to a map. So the value in this case is the stack trace of my program, and the key is that byte of memory I just initialized. The second argument here, the 1, is called skip. It's telling the profile to omit the actual call to myprofile.add from the stack trace. So when I look at this in my web browser, if I look at it in pprof, I'm not going to see the call to profile.add. We're just going to omit that. If I want to omit even more, that can pass on a higher state value. If I want to keep everything, just pass 0. So pretty simple. I found that I wasn't getting enough contention, so I just added sleep here to make things easier for demos. Pay no attention to the name behind the curtain. And then at the end, we're just going to return a function to remove my key. So this map value, again, from the map of stacks that are active. And then using this, I just go ahead and do defer, call track request, and call the function that's returned. So it's a one-liner to add to my handlers. And I get free request directing. So here's what that looks like if we list out the handler. You can see I've got one associated with that defer track request call. So there's one active request at the time that I took this profile. One thing that kind of sucks about this pattern is I do have to add my track request function call to every single handler. If I use a middleware, then I'm not going to have the function that I'm looking at associated with stack trace. It's just going to be an anonymous function. And that's not really helpful because we want to be able to do this without having to explicitly define every single handler. That's boilerplate we don't need. So it's an unfortunate limitation where you can't actually see what requests are active right now if you want to do an API. So this is a little bit of a contrived example, but I'm going to talk about what we can do to fix that in the future in a little bit. So if we can't use it for request tracking right now, what can we use custom profiles for? Any critical resource in your application is a good candidate for custom profiling. You've got open files that you're doing I/O against. You've got connections to a database that you want to monitor, network sockets you're interacting with. You've got a pool of work routines that are bound to a certain like be active. These are all good candidates for custom profiling. Anything that helps you identify a resource leak, or if you're trying to measure contention in your application. So we've got a bounded resource that our program is going to work on. Being able to measure how many of them are active lets us know if we need to increase the amount of parallelism or decrease it. Maybe we've gone too high. So we can actually instrument our programs and make sure that we're setting sane values for the size of our worker pools or our resources, and not letting them go to infinite values unnecessarily. So as part of this, I wanted to talk about what we can actually do with custom profiles in a sense that was real. I had never used these before, and so as part of my presentation, I actually went and added support for tracking pending query requests in our services at VividCortex. So now there's a feature flag in all of our services that let me basically turn on tracking for how many pending db.query operations are there in our application at any point in time. And so down below, you can see a web output call graph of which functions are calling db.query in one of our services. This is our time series directory service. It's very important. It tells us where all the data lives. If it goes down or is under high contention, then we can't find our data. So we need to have this active and responsive at all times. And so you can see at the moment that I grabbed this was actually from production. So I was kind of surprised. There were only 3 query operations going on at the same time. And you can see the function names. It's a little hard to read here, but right here we've got get cluster partition. So this is the actual function that is looking up where a partition of data in our time series service lives. And on the side, we've got a middleware function to tell us which customer is associated with the request. So I can track and make sure that we're not getting slammed in the directory service. And if we do, I can either spin up another copy of it or add more open database connections. Just open up a lid there, set db.max open connections to a higher value. So that was pretty cool. I'm actually going to be doing a lunch and learn, I think, next week at VividCortex to show my coworkers how this works. Because when they saw the code review, they're like, wait, what is this? So it's always nice to learn something while you're getting ready for presentation. So wrapping up here, I think I'm running out of time. Yep, so we'll go quick. What's next for pprof? I scoured the GitHub issues list to just see what kind of pending proposals there were. Picked out a few that sounded interesting. The first 2 are not accepted yet, but they're still under discussion. Supporting tracking file descriptors natively, so that'll be really cool. Anytime you've got an open file descriptor, you can track it and keep off the runtime. This will probably be set up the same way as mutex and POC profiling versus disabled by default. We enable it with a runtime function. The other one is profiling non-heap memory. So heap profiling only looks at stuff that's allocated on the heap. There's a lot of sources of stack memory though that can cause our program usage to go way up. So we want to be able to get visibility to that as well. So that's another pending request that you need to make a decision on as a community. The second 2 are actually accepted proposals. They both have Go 1.9 milestones. Again, I'm not sure if they're going to get in or not. We'll see. So count-oriented custom profiles. This is basically allowing us to track the usage of a resource over time. So right now, we can do what's called an in-use profile. I can see instantaneously in my program how many of X resource are currently active. I want to be able to see, how many times has each endpoint in my service called db.query over time look at emergent behavior versus instantaneous behavior. I would have to remove that profile.remove call that we saw in the demo. That would give me an infinitely growing map. That is a bad idea for a service. So there's a proposed change to basically create a counter version of this where I can just count the merge stacks that we've seen since this program started. And that'll allow me to do that emergent behavior and see, okay, where are most of the queries coming from? What endpoints are most active? Where is most of my behavior coming from my application? And the last one, this is really cool, and it solves the tracking active requests through middleware problem that we talked about earlier. So supporting profiles with labels. This is basically expanding the context work that's been done in net/HTTP and database/legal into pprof as well. So the concept is we'll be able to specify a label or a context with our profiles, so I can associate my stack trace or my function with a piece of user data. That can be things like a customer ID. So here's the customer that I was processing when I did this request and added the stack. It could be something like the name of a function handler. So that way I can use middleware to just say, I'm going to call this function, here's its name. When I profile it, I want this label associated with it. And that way I can track, what are my handlers actually doing in the application rather than just seeing anonymous function calls. So this has a lot of really cool applications to it. I'm really excited to see this go in and see what we'll do with it because it'll allow us to really profile everything. We won't be limited by just with the call stack colors. We can do a lot more with anonymous functions and middleware chaining and still get all the visibility on pprof that we want to get. So that's it for me. Here's a link to my GitHub repository. It's got all the demo code that I didn't show you. It's well commented examples of how to use pprof in different scenarios. There's also a client app in there just to basically query different endpoints in a loop. So yeah, that's it. Thanks. I don't know if we have time for questions or not. We got a minute or two.
Does anyone have a burning question?
One burning question first.
Can you collect mutex and a blocking profile at the same time? Do anything interesting with that?
So the question is, can you collect a mutex and blocking profile at the same time? There's nothing that prevents you from doing it. However, I'll say that when you do profiling like that, there is a non-zero amount of overhead for collecting profiles. And enabling two at the same time, they're likely to pick up on each other. I don't know what kind of concurrency parameters are under the hood for collecting that information, but you might start seeing inflated results from that. So one of the general rules of thumb is only try to do one type of profiling at a time, because otherwise the two can start to skew each other. All right, thanks.